When we're trying to analyze a complex random system with all sorts of dependencies between the individual random variables, it can be hard to know where to start. The goal of this video is to give some general guidelines which I hope will steer you in the right direction. In more intricate probability models, it's very easy to get lost unless you have a clear overall strategy. So watch this video and then try to answer the practical assignment, and when you're answering it, remember the strategies that we're using here. The starting point is to draw out a causal diagram. This is a nice at-a-glance way to visualize all the random variables and how they depend on each other. Next, write out the probability expression you want to calculate. Then, the overarching strategy is this: wrangle the probability expression you want to calculate into the form likelihood of a child node conditional on its parents. Let's look at some examples to flesh out this strategy. Here's a very simple example. Find the likelihood of x when the random variable big X is generated by a two-step process like this. First generate k, then generate x based on k. We've used this sort of model many times, for example, our Gaussian mixture model from the very beginning of the course. We know how to answer the question, of course, but I want to write out the solution again to show more clearly how it's part of our general strategy. The specific tactic we'll be using here is, if the parents aren't already in there, use conditioning to incorporate them. Here, we want to calculate the likelihood of x, and so we'll condition on the parent of x, i.e. on k. The law of total probability is how we actually do conditioning. Okay, so there's nothing new here, except to understand that the law of total probability is simply the mechanism by which we achieve likelihood of child node conditional on its parents. Next, a slightly more sophisticated example of the same trick. Find the likelihood of x conditional on A. We want to know about x, so the general strategy says we need to get x's parents into the expression. We've already got parent A, but we don't have B, so we'll condition on B using the law of total probability, this time with baggage. I should also note I'm being a bit sloppy with notation here. It's a real drag to have to write out every little detail all the time when it's obvious from the context, so here I've dropped the subscripts and I'm using shorthand for the conditions. What I really mean is this long-winded expression here. Okay, so what do we do with it? We can simplify the second term here. It asks for the likelihood of B conditional on A, but the causal diagram tells us that A and B were generated independently, so A has no bearing on B, so this is just the plain likelihood of B. Let's look at another example, again with this same sort of crossing out irrelevant conditions. In this more complicated setup, find the likelihood of y given A and B. Our first step should be make sure the parents are there. We want to know about y. Y's parent is x, so we'd better put x in there by conditioning. The next step is to cross off irrelevant conditions. This comes from the causal diagram. It tells us that y was generated directly from x, so once we know x, the values of A and B are irrelevant. This is called memorylessness. It's a more general version of the memorylessness property we use for Markov chains. More general because this is a statement about random variables with any number of parents, whereas with Markov chains there was only ever one parent. You should be able to just look at a causal diagram and read off the places where you can apply memorylessness. But I don't want it to seem like magic, so here's a very quick derivation. What's the likelihood of y conditional on x and A and B? Let's just expand the conditional probability. This is the likelihood of all four of them divided by the likelihood of the condition. Next, simply write out the joint likelihood. This is where the structure of the causal diagram comes in. The whole point of the causal diagram is that it's nothing more than shorthand for specifying the joint likelihood function, and for this diagram, here's the joint likelihood that it specifies. Most of the terms cancel, and we're just left with the likelihood of y given x. As I said, you should be able to read off memorylessness direct from the causal diagram. But if you're stuck with a more complicated problem where it's not obvious what to do, this brute force method of writing out the full joint likelihood can help. Okay, let's look at another common pattern. Find the likelihood of k conditional on x. We've seen this lots of times already. This is just Bayes' rule. And the reason we use Bayes' rule is so that we can do what the general strategy tells us to do. Wrestle it into the form likelihood of a child node conditional on its parents. Where does Bayes' rule come from? It's just the same sort of derivation we had a moment ago when we derived memorylessness. Expand the conditional probability, write out the joint likelihood in full. Here, the expression doesn't simplify, and we're left with a non-k term, which I'll call kappa. The job of kappa is simply to make the likelihood sum to 1. Remember, be careful about what sum we're talking about here. This expression is asking for the likelihood of little k, i.e. it's a function of k, and when I sum up over k, I have to get the answer 1. So when we say kappa is a constant, what we really mean is kappa doesn't depend on k, although it certainly does depend on x. Okay, here's another example. Find the likelihood of y conditional on x. First rule, condition on parents. Here I want to know about y, so I had better include its parent, theta. Next, memorylessness. Once I know theta, that's all that's relevant when it comes to y. Next, we have this pesky likelihood of theta given x term, which is the wrong way around. The general strategy says we want the likelihood of a child conditional on its parents, but here we have the likelihood of parent theta conditional on its child x, so we need to flip it around. We just use Bayes' rule to flip it into terms that are the right way around. The whole point of this procedure is that every single one of these terms that we've ended up with are things that we can read off directly from the question. There'll be text in the problem setup or code that says, here is the prior for theta. Here is how x was generated from theta. Here is how y was generated from theta. These links are called causal links. They're the edges in the causal diagram. The diagram reminds us what the causal links are that the question provides us with. When we're asked to calculate something, we just have to wrestle with it until it's in the form where we can just plug in the causal links from the question. Here's one last example. This is a question from an earlier exercise. Find the likelihood of h conditional on x and y. First step, we've got x and y in here, but we don't have all their parents, so a better condition on the missing parent m. This is just using the law of total probability, this time with baggage x and y. Next, it's a bit tricky to see exactly what to do, so I'm just going to use brute force expansion. That's what was behind memorylessness and behind Bayes' rule, so if there's any clever use of either of those two, we're going to find it via this brute force expansion. I'll expand both the conditional likelihoods. This is good. It cancels nicely, and we're left with just a joint likelihood. I'm just going to do a brute force expansion of this joint likelihood by reading it off the causal diagram. And I'm writing kappa for the term at the front. This term doesn't involve h, so as far as the distribution we care about here is concerned, it's a constant. And we've ended up with an expression which involves just the causal links, the ingredients that have to be given to us in the question. From here, it's simply a matter of plugging in the conditional probabilities that the question tells us, and then finding the right way to solve the sum over m and to find the constant. Those steps will be different in each case. The practical assignment will ask you to infer the location of a scampering stoat based on noisy readings of its location. You'll have to do some probability wrangling very similar to what we've got here. And then, to find the constant kappa and to do the sum over m, you'll actually use a mixture of Monte Carlo and computational Bayes.